So in the first part of the lecture, we talked about how to formalize the actual coordination compounds in terms of chemistry. So how do you arrange them? How do you call them? What are all the formalism? What makes a complex stable? How do you get the oxidation states? And so on and so forth. Now that this is cleared, we can actually concentrate a bit more on does this coordination chemistry mean in terms, especially in this case, of the metal sites that is at the center of the coordination. Fundamentally, a complex is something that is a bit more convoluted than an organic molecule that we have seen before. So you want a metal in the center and something that is coordinating around the metal. So your ligand, which is the something that is coordinating around the metal, is actually bonding with the metal center through usually a lone pair. So there must be a lone pair in your ligand in some shape or form. It could be the lone pair of electronic configuration that is unfulfilled, so it will be an ion, or for instance, in the case of ammonia, is the actual lone pair that comes up from the coordination, like from the bonding of ammonia within itself. So you could approximate the idea of ammonia bonding through the lone pair in a bit of an old school, basic high school approach in which you just use the sp3 hybridization of the ammonia molecule that is tetrahedral. At that point, you get 4 sp3 hybrids that in the formalism of hybridization are all supposed to be at the same energy. One of them is a lone pair, so you will use this one. But what we are saying with this approximation is that all of these electrons are energy equivalent, so this lone pair could be equivalently located in any of the sp3 that generate orbitals equivalently. This is limited as an approximation, and as inorganic chemistry is building on the theory of general chemistry, in which we learned about the salts, we can actually derive a better approximation of the internal bonding of ammonia using a natural molecular orbital diagram, in which we fundamentally approximate all of the bonds with the sigma bonding within this geometry. So you end up with the sets that you actually want to bond. And on the basis of these sets, you mix this hydrogen and all of the nitrogen orbitals to derive an actual molecular orbital diagram. This gives you the same number of bonding molecular orbitals, obviously, but this time you actually had the staggering in energy. Not all of these are equivalent in energy. So you end up with 4 bonding molecular orbital, of which these 3 are all in the shell. But then you have the lone pair that is isolated in energy, and it is the highest occupied molecular orbital available, almost, like it's basically non-bonding, available to ammonia. So ammonia is bonding with this molecular orbital. It is not equivalent to the other one, but it is the one that is doing the bonding. So every time we're looking at the interaction, if we want to know what is the interaction of the ligand, we actually need to get the frontier orbital, so the highest possible one available either of the atom or of the molecule. It doesn't matter what the rest of the molecule is doing, not really at this stage. You know that the last thing that is interacting will be this point bonding into the metal. So this one is the one that you use to do all of your other considerations. So we need to be able to get the molecular orbital. I will advise you to re-exercise the salks and the derivation of molecular orbital diagrams of sensible molecules from salks using also ammonia as an example, including getting the labels. The question here is, if we know what ammonia is doing and how is it bonding, what orbital is it using, what electron is it using, what is the metal doing? So the metal is here. What is going on? how is the metal arranging itself in the center, how is it interacting with all of these ligands, and why should we assume that the metal is doing anything to begin with. So first of all, usually when you have a complex, you are using transition metals. So the whole theory around coordination compounds is usually built around transition metal elements, because they are the ones that tend to do the most variety of complexes, and at the end you can actually expand the whole theory accordingly. Unlike something like ammonia, in which you only have s and p orbitals because you're using main group elements, in transition metals, your valence shell is identified by d orbitals. So the d set is characterized by 5 orbitals, all degenerate in energy. They are more localized than the s and the p orbitals. You cannot use the useful but limited approximation of the sp hybrids. Doing an spd hybrid is fundamentally incorrect. The d orbitals do not have the correct energy and the correct localization in space to be able to have a functional approximation, like you can just consider them to be the same orbital. So you need to always consider them to be by themselves, fundamentally. So you have 5 different d orbitals with a very specific directionality in space. This comes from the solution of the Schrödinger equation, including which nodes do you end up having. So 3 of them are going to be in a plane, but staggering in the plane of the Cartesian axis. And then you have 2 that are the dx squared minus y squared that are bisecting the Cartesian plane. So this can only be by itself. And this square that is pointed in the z direction. So these are very complex directionality features that are way more convoluted than the px, py, pz that you will have in the p set, or the sphere that is the s set. This is something that we need to take into account because the d orbitals will interact differently and will behave differently depending on the geometry that you put to the complex. Why does the geometry make a difference? Because the energetic of the system will change depending on what is your system doing around these d orbitals. So the directionality will influence the energies of these d orbitals that start as degenerate. So if we use the most stereotypical geometries of like basic transition metal complexes, your cornerstones are on one side the octahedral geometry, on the other side the tetrahedral geometry. So if we use the octahedral geometry and we want to get ourselves the set, the symmetry set of what are the d orbitals doing and how do they behave against the symmetry of an octahedron, first of all, we need to recognize that a shape like this, in which, mind you, all of the sides are at the equivalent distance from the center, belongs to the OH point group. The OH point group has the following symmetry operation and is characterized by the following character table. So all the transformations that can be done in the OH point group belong to the character table. All of the orbitals appear together. You cannot say, oh, I only want my complex to have this square, because all of the d orbitals come together with the atom. Therefore, when you actually do the set of what is bonding in an octahedron, you need to consider all of them at the same time. So if we apply the reduction formula, so we try to figure out how do all of these elements transform against all of the symmetry operation of the point group. We can apply the reduction formula, but we can also try to be logical about it. So applying the reduction formula will tell you that all of these transformations are belonging to 2 sets. One set of EG and the other one that is T2G. So they belong to these labels over here. we can simplify our life and not try to do the full decomposition against everything on the basis of how is the symmetry behaving in this thing. For sure, it cannot be a total symmetric representation because these are not spheres. So they do have a directionality. They cannot belong to a total symmetric representation. There are some of these representations that are anti-symmetric against the center of symmetry. All of these orbitals are symmetric around the center of symmetry, the center of inversion of the octahedron, which means you're only looking at EG labels. Fundamentally, then you subdivide the set on the basis of, you can already see how the set subdivides itself on the basis of the behavior against the main symmetry axis and how many redundancies do you have in the set. Remember that the Mulliken symbols that we revised also as a part of lecture 0 have a meaning that is perfectly reflected in these sets that you end up having. So the EG set belongs to these two, and the T2G set belongs to these two. In tetrahedral geometry, your arrangement in space can be more easily summarized if you consider the corner of a cube, and then you stagger the corners that you're considering. So either these two corners versus these two corners, or the flip version, but basically you're bonding a tetrahedron with a metal in the center and then all the bonds going towards the sides. Once again, all of the orbitals are coming together. A geometry like a tetrahedron belongs to the tetrahedral point group that has the following symmetry operation and the following point group table. If we apply the reduction formula, we can, once again, ignore the total symmetric representation. It is impossible that these orbitals are total symmetric and just decompose against the other representation. In tetrahedral, if you actually apply the reduction formula, you end up with an E set and a T2 set. Note how you don't have the G labels because a tetrahedron does not have a center of inversion. So these ones need to be separate of each other. Now, how do we know how these sets separate themselves in space? This is something that the symmetry label are not going to tell you because the separation in energy is something that depends on how the bonds are arranged around the orbitals. So conceptually, in what is called the crystal field theory, the theory is that you have your isolated atoms with all your 5 d orbitals completely degenerate. If these orbitals were placed in a spherical field of electrostatic potential, so all of them are affected equally from the electrostatic potential around it, the set will rise all together because the interaction is equivalent. If your electrostatic interaction, instead of being spherical, is directional, which is exactly what happens in the moment you have actual ligands in a certain geometry around your metal, there will be a split in energy, and not all of this will be affected equivalently. So there will be some that are more affected that will rise in energy, some that are less affected that will drop in energy. If your geometry is like this, the set will split in one way. If your geometry is different, the split will also change accordingly. So if we go into the octahedral geometry, once again, what you are saying here is that the orbitals that point directly in the direction of the ligand are dz square and dx square minus y square, because you can see that the lobes of the orbitals point exactly in the direction of the ligand once you define the proper Cartesian arrangement. This means that your EG set is higher in energy than the barycenter of the free ion. Meanwhile, the T2G set, which is everything else, points midway through the direction of the ligand. So it's not going to be equally affected in energy. It will drop in energy in comparison to the barycenter in which all of the 5 are equivalently placed. But since you started with 5 of them, the gain and the drop needs to be proportional. So if 2 are rising and 3 are dropping, you cannot do half and half because you did not split it in half and half. You split 2/5, 2/3. So you can see that this is proportional. So if this is the entire octahedral splitting, which is what we call the octahedral field splitting, because you put your orbitals in an octahedral field, the 2/5, 3/5 shift is proportional in height. So it's not halfway through, which will be here. This is slightly higher, this is slightly lower. So this is what we call the octahedral field splitting. And this is how you actually divide the energies. So we started with 5 degenerate orbitals. The 5 degenerate orbitals are not degenerate anymore, which means when you're going for the occupation will follow. It will start from the lower energy, and then it will go to the higher energy. You cannot consider all the 5d orbitals to be equivalent in terms of energy. In a tetrahedral geometry, you have the opposite situation, the one that are more directly interacting with the ligands, so they are closer to the electrostatic interactions that you're going to get with the ligands, are the T2 set, so every bisecting orbital, so dxz, dyz, dxy. The E set, so the dz square and the dx square minus y square, are the further away from the electrostatic interaction of the ligands, so they will drop in energy. So a tetrahedral field splitting will have 3 orbitals on top, 2 orbitals at the bottom. Once again, proportionality of 3/5 to 5th split, like flipped around in comparison to the octahedron. So you have 2 at the bottom, 3 at the top. In proportion to each other, the entity of the crystal field splitting, so this span in energy with which you open up the field splitting, is not equivalent. So they don't drop and rise in the same way on the basis of the octahedral field splitting has 2 orbitals that point directly at the ligand. They literally profile the bond arrangement, which means the gain and the loss is going to be broader than the one that you will get in a tetrahedral geometry, in which, yes, we could see the conceptual electrostatic interaction, but we could also see that none of the orbitals by themselves were lying in the direction of the bond, which means the drop and the rise is more modest in comparison to the octahedral. How modest? By rule, in equivalent complexes, fundamentally, a tetrahedral geometry is 4/9 of the octahedral geometry. So if you want to know how big this is, if you have this that is 1, this thing is 4/9. So it will always be smaller. Note that how big is the field splitting is something that you cannot define in a vacuum. You need to be able to consider the metal oxidation state, what is the metal doing, and what are the ligand exerting in terms of gain and loss. So what is the influence of the ligand? At this stage, we are not doing the full what is the influence of the ligand. This is going to be part of lecture 2. But we know already that the influences of the metal oxidation state means that if you have a metal with higher oxidation state, the delta will be higher. And if you're going down in the group, you end up having something bigger and bigger and bigger. This is related to how diffuse the orbitals are. When you go and fill, you need to consider that having to cross this delta is an energy requirement. So if this delta is too big, you might end up having an advantage in filling this set first or filling all of them in sequence. So either you put your electron 1, 1, 1, 1, 1, Or if you still have 5, you put 1, 2, 3, 4, 5 instead of going up. This is the difference between what is called a high spin configuration, in which you try to maximize how many orbitals you're occupying, versus a low spin configuration. This is relevant in the case of an octahedron, because this crystal field splitting could be remarkably big. Is never relevant in the case of a tetrahedral complex on the basis of, since you have a fortnight relationship, the tetrahedral crystal field splitting is always low enough to demand that you arrange your electrons in a high spin configuration. So you're never going to have something with 4 electrons to place in which you place 1, 2, 3, 4. It's never going to happen. You're always going to do 1, 2, 3, and 4 in high spin configuration. Once you actually form the complex, the advantage of making a complex, and the reason why we think the metal is doing something, is that the energy advantage is the configuration that is actually keeping the metal complex stable. You would prefer to be complexed, because the complexation will give you an energy advantage upon actually distributing the electrons in the morphed crystal field splitting arrangement. How much of an advantage do you have? Well, it will depend on how many electrons did you place in which orbitals. So you would proportionate the advantage with the number of electrons in the T2G set versus the number of electrons in the EG set, knowing that you are splitting this delta. The delta is a value that either you have to have or you have to assume in proportion against something. This is not something that you can know from first principle, but you know that the moment you have the arrangement and you have the configuration to place, everything that you put in the T2G set will give you an energy advantage. Everything that you put in the EG set will counter slightly this energy advantage. In the tetrahedral, it's the same formula, but you flip the other way around and you use the E set versus the T2 set. The same business, you're supposed to have a crystal field stabilization energy, which is this acronym. So the energy that you get by arranging the complex. So a good example would be if you have the hexachinoferrate ion, which is a high spin D5 configuration, you end up putting your electrons 1, 2, 3, 4, 5 with a crystal field stabilization energy that at this point goes to 0. They will nullify each other, but it will be happy to be distributed off. Whereas in the hexaamino cobaltate, which is the ion that we already saw before and we named it before, you have still an octahedral complex, so the arrangement of the orbitals is exactly the same, but now you have one more electron. And if you go into low spin configuration, you end up with all of them filled. With all of them filled, you have a very strong stabilization energy that is negative. This, the delta O, will be different in the two complexes because the metal are different, though they have the same oxidation state, and they are in the same period, so it might not be that much difference in terms of the influence of the metal. The ligand is different. We don't know yet what is the effect of the ligand, but we know that the ligand is going to make a difference. There is an additional feature to consider. At the moment, we were looking only at perfect geometry, so a perfect octahedron and a perfect tetrahedron as the cornerstones of our geometrical arrangement. You can have modification of the original coordination that are triggered by the specific electron configuration. So the theorem of Jahn-Teller is the one that states that if you have a degenerate system, your system is not going to be stable. So if you want it stable and your molecule is not linear, your molecule will do everything in its power to try to remove the degeneracy. So if you have an octahedral system, the degenerate orbitals are these three and these two. If you end up with some degeneracy in these two sets, so for instance, there is one electron here, one electron here, you will try to remove the degeneracy. The easiest way to remove the degeneracy is to influence the bonding. So the reason these sets are equivalent is because everything here is at the same distance. If the distances are different, so if one bond, for instance, is elongated axially, your Z direction, which is the one that affects the dz square, will drop in energy because now the dz square orbital is further away from the ligand, so it's feeling less electrostatic interaction. On the other hand, if you were to do axial compression, you end up dropping, so you close here, you elongate on the basis, you end up getting the dz square minus y square at a lower energy. Note that whatever you do here will also have a commensurate impact on the bottom sets. Because inevitably, if this one is affected, then this one is also affected, and so on and so forth. So everything you do carries out on the other one. Some of the electron configurations are completely immune from Jahn-Teller, on the basis of if there is no degeneracy, you are not going to try to remove it. There is nothing you can do to really remove it. So if you have something, for instance, like the D5 high spin that we've seen before, it's not really degenerate, or like the low spin D6 that we've seen before with the hexamino cobaltate. All of the orbitals in the lower set are occupied. There is nothing for you to do. There is no movement that you will do here that will gain you any advantage, because you need to notice how every time you rise and you drop, so this will affect the energy. So let's look at some of the systems with a Jahn-Teller distortion, which, for instance, as a stereotypical one would be copper, like a Nexa Aqua copper 2, which is a D9 system. D9 systems are the Jahn-Teller distortion systems. The degeneracy comes from the option of having two different ways to fill in the electron configuration. So on this set, either you feel like this or you feel like this. All of these configurations are equivalent in energy. This comes from the EG set redundancy. How do you remove the redundancy? If this is how you started with, if you elongate on the z-axis, then the z-axis drops, the x square minus y square set rises. Since you started with two orbitals, your split is even. This time is actually even. Commensurately, the bottom set, even though it's completely full and will be unaffected by the degeneracy, will split, but this time, since one goes up and two go down, then you have a 2/3, 1/3 opening. When you go and fill in your orbitals, your electrons in the orbitals, you can notice now how the single electron without the pair has its own orbital in a unique energy state that is unaffected by any degeneracy. So you have removed the degeneracy and actually made the complex more stable. Can we prove that this thing is more stable? So if we do the energy of the octahedral system, undistorted as it was before, and then we do the energy count of the distorted system, so we consider all of this gain, drop, we can know already that this one is going to cancel out itself to zero, because you have two things on a 2/3, four things on a 1/3, they're going to cancel each other out. And this one, you can already solve it on the basis of the undistorted one. So you know that you have basically an undistorted octahedral crystal field stabilization energy with one element that is different, which is this energy gain. So in comparison to what you had before, a Young-Teller distortion gives you this half of a fraction advantage over the whole system. So this time, as you distort the system, you get an extra energy added to the stabilization, which means a distorted copper complex with the aqua ligand is going to be more stable than an undistorted one, which means you cannot stop the complex from trying to achieve destabilization. So experimentally, when you actually go and measure these complexes, you're going to notice that the long axis, so the one that is on the Z direction, is going to be 0.45 angstrom longer than the other axis. So the complex is actually distorted and elongating in the Z direction. I would like to clarify a couple of things on the crystal field stabilization energy and the Young-Teller distortion. You have two competing effects here. The crystal field stabilization energy is one thing, so this opening up and trying to fill up all of the orbitals. Pairing the electrons instead of leaving them unpaired actually carries an additional energy penalty. To pair the spins instead of leave them unpaired and completely parallel in spin to each other requires you energy. So sometimes your system will not do that because the pairing energy that will take you to flip the spin and make them order downwards will be too high. So if the pairing energy is higher than the delta of the crystal field splitting, you're not going to pair the spin, your system is going to be high spin. If the pairing energy is lower than the crystal field stabilization energy splitting, you're going to pair the spin and have a low spin system. From an experimental point of view, even though we say that the Young-Teller distortion can be axial elongation or plane elongation, so either you elongate on the axis or you elongate on the plane and you squish on the axis. Usually the degeneracy that triggers a remarkable and measurable and observable Young-Teller effect is the one that affects the EG orbital. So every time you have a degeneracy there, that's the moment you trigger a Young-Teller distortion. These are the orbitals that point directly to the ligands. So obviously, those are going to be the ones that are more affected by any energy requirement because moving the ligand away from their position immediately avalances down an energy advantage. Also, this is the reason why the Z elongation is preferred in comparison to the plane elongation. Because to gain your advantage, you need to only move 2 ligands to do the Z elongation. Whereas if you want to do the plane elongation, you need to move 4. At that point, you might decide not to do it. There are some cases in which compression and elongation are completely energetically equivalent, especially at a given temperature, meaning that your complex might be breathing or it might look like it's undistorted, but is oscillating between the two distortions. You always need to consider that these are energy advantage considerations. They're not set in stone, but it's something worth considering when you're looking at a complex that contains degeneracy. No degeneracy, no problem like this. Other configurations are absolutely possible. There are a lot of very nice geometries. You've seen it also at the beginning of the lecture. So we have complexity in the complexes that is remarkable. We are going to use a lot of these other geometries and treat them properly also in tutorials, so we can touch them more and see how they correlate with each other. Depending on the metal and depending on the electron configuration, the fact that all of these other geometries are going to have a different orbital arrangement and a different energetic of the system might make one geometry more advantageous in comparison to the other, or more advantageous at a certain temperature, or more advantageous with a certain ligand, and so on and so forth. So we actually want to use our octahedral and tetrahedral as the cornerstone so that we have something with the easier geometry on the basis of the Higher symmetry. We use them as our corner, and then we derive all of the other configurations and what is the metal doing around all of the other configurations. At this point, we are there with a complex that can be built. We know that the ligands are using the frontier orbitals, so either the last point of the electron configuration of an atomic one, or the last available corner orbital available to the ligand. The metal has a pile of the orbitals that split in different sets depending on the geometry, and then it triggers an energetic advantage as it's trying to actually place the metal electron of the electron configuration. So you have these two things, you need to consider them at the same time. How do you actually enforce this bond? And can we look at a complex as a molecule? So actually have a molecular orbital diagram of the entire complex and see where is the actual energetic advantage of doing this entire charade? You can, but you actually need what is called ligand field theory instead of crystal field theory, and we're going to do this in lecture 2. These are your learning objectives for lecture 1, so make sure to go through all of them and be able to reconstruct where they come from and what can you do with them. And I'm going to see you in lecture 2, but first of all, I will see you in the Q&A that will follow the 2 tutorials that you're going to do as part of this week content. Thank you.